Imagine the early Earth. You probably picture a barren, volcanic wasteland getting absolutely pummeled by meteors. Under those conditions, biology doesn't stand much of a chance. The assumption was that our planet stayed completely uninhabitable for hundreds of millions of years, and that the very first cellular life only popped up later through an incredibly lucky sequence of random chemical collisions. But there was a massive problem with that story. Geologists and paleontologists had zero direct physical evidence to prove those lethal conditions actually existed. The rocks from that era simply aren't around anymore. Without hard data, researchers fell into a common trap. They theorized wildly to fill the void, and then became fiercely attached to their own speculations. The hellscape narrative hardened into a dogmatic consensus that went unquestioned for decades. New evidence has replaced that narrative. With the hellscape model gone, researchers are having to rethink the entire timeline for the emergence of the biosphere. The first major roadblock to early biology was the formation of the Moon. Roughly 4.5 billion years ago, a Mars-sized body slammed into Earth. The traditional assumption was that this impact vaporized the surface and kept the planet as a boiling ocean of magma for an eternity. Recent supercomputer simulations show that physics works much faster. When researchers mapped the impact at high resolution, they watched the collision blast a massive ring of debris into orbit. The models showed that debris coalescing into our moon in a matter of hours, rather than a prolonged geologic epoch. With the orbital chaos settling almost immediately, Earth's own magma oceans cooled and solidified remarkably fast. The fire and fury of our planet's infancy was fleeting. Earth stabilized quickly, shortening the time it took for the planet to become habitable. Even if the magma cooled early, there was a second assumed obstacle: the late heavy bombardment. This was a theoretical period of intense meteor strikes, thought to have completely sterilized the planet around 3.8 billion years ago. The entire theory for that bombardment rested on argon isotope analysis from moon rocks brought back by the Apollo missions. When scientists re-examined the radioisotope data, they found severe artifacting in the results. Plus, the astronauts had mostly sampled rocks from the exact same large impact basin. Once you remove the late heavy bombardment from the timeline, the physical record looks completely different. Minuscule zircon crystals recovered from Australia prove that by 4.2 billion years ago, the planet was already covered in deep, abundant liquid oceans. This shift turns the early Archean from a period of constant destruction into a stable environment for biology. And paleontology is finding physical traces of the organisms that lived in those oceans. Researchers in Quebec identified tiny iron-rich tubes and filaments trapped in rocks dating back at least 3.77 billion years, possibly deep into the 4 billion year mark. Geneticists are arriving at the exact same timeline through a completely different method. By using phylogenetics, they can build vast family trees of modern microorganisms, tracing their genetic mutations backward to find the last universal common ancestor, or LUCA. The most recent models date that single ancestor node to roughly 4.2 billion years ago. That lines up perfectly with the geological evidence for those first global oceans. But the data revealed something strange about LUCA's genome. It was highly complex, containing over 2,600 encoded proteins. It even possessed a primitive immune system designed to fight off microbial neighbors. An organism doesn't need an immune system if it's the only thing alive. LUCA had neighbors, which means it wasn't the first biological organism. The true origin point has to sit even deeper in the past. The data suggests life appeared within a 100 million year window of the first oceans, suggesting a much more rapid process than we once thought possible. This updated timeline introduces a severe mathematical problem. If life emerged within just 100 million years of the planet solidifying, it outright eliminates any origin theory that relies on the slow accumulation of random chemical events. There just wasn't enough time. Take the popular RNA world hypothesis. It assumes that complex RNA chains eventually formed through entirely random molecular collisions. But with only a 100 million year window, the odds of those precise collisions happening by pure chance drop to zero. Researchers are now forced to abandon pure luck. they have to look for highly efficient, extremely fast biological processes driven by energetic environments. Places like alkaline vents on the deep sea floor, where hot water and concentrated chemicals provide a continuous, high-pressure engine for complex reactions. In this new timeline, the origin of life looks less like a lucky accident and more like a predictable chemical consequence of the young Earth's environment. For decades, origins of life research was held back by a lack of hard data and an excess of ego. Without physical evidence to correct them, scientists bitterly defended their own rigid theories, actively shutting down or mocking dissenting views from rival laboratories. That scientific culture is finally breaking down. A new wave of researchers, organizing under groups like the Origin of Life Early Career Network, are actively rejecting that territorial approach. Instead of fighting over whether RNA or metabolism came first, they are integrating these competing ideas into single experiments and deploying artificial intelligence to map out how huge numbers of molecules interact simultaneously. Moving past the hellscape myth shows that prioritizing evidence over inherited assumptions is the only way to resolve how we actually began.